Hey gang, welcome back to 3440. Today we're going to discuss frequency distributions a little bit more and the kind of graphs we can do them. These are mainly for quantitative data, and actually they are predominantly and only for quantitative data really. And so one of the types of graphs we'll talk about today you're probably pretty familiar with, but we're going to go into the nitty gritty of it, talk about some terminology, some decisions that can be made based on them. And kind of look at a couple of different things. We'll also look at two different variations on the classic histogram that some people do use, and I will give you my feelings on where those are used and why you might or might not want to use them when we get to them. So let's get into it and check it out. So the first thing we want to do, like we did with the qualitative data, is talk about what do we do when we build a frequency distribution for quantitative, because they're slightly different in the way they're constructed. But only because with the frequency distribution table for quantitative data, that we don't have any natural categories like we did with the qualitative. And so we have to divide the data into classes. All right. Turn that to red so y'all can see it. All right. So classes are intervals of equal width that cover the values that are observed in a data set. All right, so each class will, correspond to a certain section of the data that we count. We'll end up using to make a histogram or graph that gives us the heights of our bars and say like a histogram. So each class is it's constructed of what they call a lower class limit and an upper class limit, and each one has what we call a class width. The lower class limit is just the smallest value that will actually appear in that interval. All right, so you're going to include if the lower class limit number actually, let me say that again, if the lower class limit number actually is in your data set, it will go in that interval. Okay. The upper class limit is the largest value that can appear in the data set. All right, so it's like usually it's a closed to closed interval, but when we draw them on graphs, we'll see that you don't include the upper class limit usually, unless you're doing it in Excel, because Excel is not good at drawing histograms. Yeah, I said that. I don't think it's good at it at all, and you have to do a lot of manipulation to get it to draw a histogram. If you've taken me for 3600, you kind of know that. The class width is something we get to choose as the researcher. Oftentimes, if I ask you to construct one, I'll probably tell you what to do on those, how many classes I want. Just so it's easier for me to grade, but in reality it's up to you how wide your class width. In the case of this, your class width is the difference between your class limit, your lower class limits. So from 0 to 5 means our class width is actually just 5. All right, and so that's again a choice you make, but the number of classes you have correspond to the number of what we call bars or bins are in your histogram, as we'll see later. So some general rules of thumb for choosing your class width and choosing a lower class limit for the very first class, because once we do that, the rest of it just kind of flows out based off of those two things alone. And so when you choose the class width, you can just choose any number you want, really. You can say, I want each class width to be 2 or 4 or whatever. What some people will do is they'll decide how many classes they have, and so to choose their class width, they'll just do they'll take their, they'll find the minimum value in their data set, minus, or it should be really max minus min. The maximum value in their data set minus their minimum value in the data set. Get that range, that's also what we call the range, as we'll learn later on, and divide it by the number of classes. And that'll give you your class width. All right. So if you just want to pick it based off, I want to have 10 bars in my thing, then you find the difference and you divide it by 10, the difference between the max and the min, that is, and divide by 10, and that gives you your class width. Okay. We then need to choose a lower class limit, a place to start from. Usually that is not going to be your minimum, although some people do choose the minimum for their lower class limit. I don't recommend that because it makes your interval spacing a little bit weird, and your numbering across your x-axis a little bit weird when you build a graph from it. And so to kind of keep consistency, I recommend picking the first. Now, unless your lower bound, your lowest value is an actual whole number, you can just pick that one. But if they're not and they're decimal numbers, picking the first whole number below your min is a good idea. And technology oftentimes will do this for us. We don't often have to do this. We can set up and tell it what we want our limit of our graph to be, where we want it to start on the x-axis and end at, and then we can tell it, how wide the intervals need to be for each one, and it will do that for us automatically without us having to. But that requires us knowing what that lower bound is, or what that first lower class limit is going to be. And oftentimes, again, like I said, you don't really want it to be the minimum value unless it's a whole number. Okay. So then you just compute the lower limit for the second class by adding the class width to that lower limit. This kind of makes sense, I think. And then you take and compute the lower limits for each of the remaining classes by continuing to add the lower class, or the class width, that is, by adding the class width to each one of those previous lower class limits. And you stop when you know that you're going to include the largest or the maximum data value in the last class. All right. And then you go back through and you count the numbers to get your frequency distribution. So let's use a data set that's rather large, and I will not waste your time by going through every little detail or whatnot. We'll find the frequency for one of these, and I'll just give you the rest of them, and you can double check me on it. But the emissions, the data here represents the emissions for 65 vehicles from some state where they collected this data. I don't recall where it's from exactly. But the measurements are in units of grams of particles per gallon of fuel. That's a hell of a unit. All right. I probably wouldn't put that on the graph. I'd probably just tell people that in my presentation or in a write-up somewhere. But there are ways to kind of shorthand that too. So we'll see that when I'm in the graphs later. But notice here I highlighted the minimum. So this range here is from 0.25 to 6.64. All right. So you could build a histogram in a variety of different ways, but knowing that min and that max are helpful. Since that min is 0.25, and notice all our numbers are rounded off to 2 decimal places. Our first lower class limit should probably be 0. That way we are including everything. And 0.25 to 6.64 is not a very wide range, but when you're talking about decimal numbers, you can kind of treat it kind of like it's a wide range. And so maybe a class width of 1 here would be good, because that would give us roughly about 6 or 7 classes. And so maybe that class width of 1 would work. So let's do that real quick. Let's use a class width of 1, and let's construct a frequency distribution using a class width of 1 for the emissions data. This is pretty straightforward. Remember, I said I'm going to choose my very first class limit to be 0. And the reason I did that was because my minimum data value was 0.25. But notice I'm writing it down as 0.00. There is a reason for this. Okay. Now, since the class width is 1, according to the general rules of constructing one of these, I just have to add 1 to each class limit. So I got 0.0, or lower class limit. So 0.00, my next lower class limit is 1.00. So I'm just adding 1 as I go. The next one, you probably guessed it, is 2.00. I'm just adding 1. 3, 4, 5, and then finally 6. Okay. My upper class limit is going to be the number that comes right before the next lower class limit. So your upper class limit should be kind of go in tandem here. So my upper class limit here should be 0.99, because that's the value that comes in just shy of 1.00. And then again, the same thing with the next upper class limit. I want that one to be right before 2, so this should be 1.99. And then you kind of see the trend going here. Now I'm just adding 1 to my upper class limits. All right, so that's here. So this one here, its upper class limit has to come before the 3 in the next row down. And so this should be 2.99. Now, keep the same color here. And we just keep going down the line. I bet you can guess this one's going to be 3.99, 4.99, 5.99, and 6.99. This should probably go without saying, even though it was in the rules. It said we stop when we get to the when we get a class that includes the largest value in the data set or the maximum. Since our biggest data value is 6.64, we can stop at the the class that has the limit 6 to 6.99 because it includes that. You don't have to keep going. Stop where you got to stop. Okay. Now we just need to count and get the frequencies here. Let's do it for the first class only, the 0 to 0.99 class. So we're going to go back to that data on the previous slide, and let's count and ensure and see what our frequencies are. Our frequency is for that class, that is. So I'm just looking for the ones. I'm going to erase this stuff here. We're looking for anything. Nice thing about this is they're decimals. So if you put a leading 0 in front of things, we're looking for all the numbers that have a leading 0 before the decimal. And so we've got 1, 2, 3, 4, 5. It's going by columns 6, 7, 8, and 9. Yep, that's all of them. There's 9 there. So my frequency is just 9. And so, just to not bore you with counting the rest of them, we go through then and count the ones from 1 to 1 point, all the numbers that are as small as 1 exactly and up to 1.99. And those would be there's going to be 26 of those in the data set. There'll be 11 of the ones between 2 and 2.99, 13 here, 3 between 4 and 4.99. Frequency should be 1 between 5 and 5.99, and between 6 and 6.99 we should have exactly 2. Matter of fact, that 6.64 should be one of them, and we should have one other value in there, and we do 6.55 in there, so there are exactly 2 of those. Again, double check me on that if you need to. We can also create a relative frequency distribution chart, because again, with histograms and other types of graphs, as we saw with the bar graph specifically, we can have them either scaled in by the frequency or by the relative frequency. So I'm just going to copy these down from the previous slide. We don't need to talk about the frequency itself again because we just did that. But let's see, this should be 3, 1, 2. All right, and then so the relative frequency, remember, there were 65 values in this data set. So the sum of all frequencies here equals 65, or another way to say that is little n, the sample size, is 65. All right, so that's the number we want to use to divide each frequency by to get our relative frequency. So here we'll do 9 over 65. And we're going to round about 3 decimal places on this one. Not for any specific reason, just because I arbitrarily chose 3. You could round to 2, you could round to 4 decimal places. It's really your preference in most cases. If I ask you to round a specific number for the relative frequency, it's only for grading purposes, but in real life you kind of get to make that choice yourself. All right, and so we just kind of go down the line here. I won't bore you with the calculations of these all the way. And so the rest of these in order is 0.400. Preferentially for me, I don't care if you just write this as 0.4. But from a visual standpoint, if you're going to include these numbers on a graph, you probably want to write it as 0.400 to make it match with your other numbers, just to be uniform, because it kind of looks sloppy when you don't. You might not think so, but I guarantee you other people do. And the last thing you want somebody to do while you're trying to just talk about your data is making fun of your graphs. Trust me, statisticians and mathematicians are bad about making fun of people's graphs when they do them incorrectly, and we're going to do a whole lecture on that specifically here shortly. Okay, so there are relative frequencies. Now we can build either a frequency graph or a relative frequency graph and kind of move on with that. All right, so let's move on to that and talk about histograms in general. So once we've created those kind of charts by hand, we could construct a histogram. Again, I'm not going to make you do these by hand. We're going to do them with our programs later in the semester. But these are primarily for quantitative data. You never make a histogram for categorical data. It just doesn't work. I've seen some people online do some histograms in R or bar plots in R, and then doing them with data that's not appropriate for it. You can do them with data that it's not appropriate for, but it doesn't always make sense. All right, it's kind of hard to do a histogram for qualitative data anyway, because it doesn't know how to break up the classes if the classes are words, right, or labels or categories. But a histogram could technically, a bar graph could actually technically be used either way, and we'll see an example of that here in a moment. But a few things about the the anatomy, if you will, of the histogram is each one of these bars represents the endpoints here. From here to here represent the class width. I also call these things bins. I mean, imagine like they're trash bins. This is where we're throwing our numbers in and separating them out, all right? Or maybe these are more like recycling bins, if you will, all right? And then the height of each one represents your, again, just like in a bar graph, your frequency or relative frequency. So here's two I created in R, a frequency and a relative frequency for that emissions data. And they have the same shape. And the only difference is the scale on the vertical axis and the values that we have at the top of each bar. We've got the frequencies highlighted above here on the particular emissions one, and the relative frequencies over here. Now again, you don't have to label these the way I did. Matter of fact, I found that it'd be kind of a challenge for the histogram. It was easier in R to do it with the bar graphs that I showed you last lecture, but it's a little harder here with these, and so I probably won't force you to give me the heights, the numbers on the bar. I'll show you an example of how to do it, but not require that you do it. But it's good practice to learn how to do these things. Notice I did try to put the actual unit measure here, and I just call it grams per gallons of fuel. I didn't get really specific here. So that's not necessary. But again, notice also that these are continuous versus the bar graph we looked at, which had gaps between it because they were spaced out. That's because these are primarily for, again, numerical data, really, quantitative data. And so the bars should be aligning and touch one another unless, like, for example, one of these bars had no values in our data set in it. Then you could have, like, say this one with 1 right here. If that was nothing there between 5 and 5.99, this would just be a flat line here, and we wouldn't have this stuff here, and it would say 0. It's okay to have a gap that way if you're missing something, but you want your data to be continuous. I have seen graphs where people have somehow constructed them and were able to skip this section entirely. We shouldn't have that issue in this course, but by hand, I've seen people do it where they go 4 to 6 to 7, and they'll have slid this entire bar over one to make it touch the other one, just so it looks like a histogram. But then the scales are all off and it doesn't look right. So your scaling down here on the x-axis definitely needs to be a continuation of from one number to the next. You don't want to skip anything. A little word about the number of classes or the number of bins we choose. The number of classes can definitely affect the overall shape of the histogram, and ultimately, as a statistician or somebody looking at data in general, and you build one of these, you're looking at it to look at what the shape of the distribution looks like, because the distribution is important because it tells us ways that we can deal with that distribution, and also tells a story about it. I'm very passionate about graphs. I love statistical graphs that tell a good story. And so if you can tell a story from your graph, you're doing them right. When you're missing details, your story's not as clear. And so to have too few classes, you lack detail in your histogram, just like the one here on the right. It's only 4 classes. It looks like almost like the Pareto chart we saw with the bar graphs. But it really makes that thing definitively skewed. And notice the tail, there's what I call the tail. We'll go over this a little bit more in a minute. It's like dropping off as you go from left to right. So it's dropping off on the right. That's the kind of thing you want to notice about that. But there's not any other detail. We don't see, we see a spike between 0 and 2 and 2 to 4, and it's not really telling us a whole lot about how our data is shaped over the entirety of between 0 and 7. The other thing is, if you pick too many classes, you get so much detail that your data is obscured. You lose things. So this one here on the left has, I'm not kidding, has 70 bins in it. It's been divided up. I believe the class width I made for this one's 0.1, because the limit's between 0 to 7. So every bin represents a width of 0.1, so 0 to 0.09, if you will, and then 1 to 1 point, it gets silly. And so the gaps there are not bad gaps that we see where we have a bunch of, there's just everywhere there's not a bar in this graph. No bar represents there was nothing to fit in those little small intervals. And while this looks similar to the graphs on this page, you kind of have a high point on the right hand side of the graph, and it falls off and does some funky stuff as we go to the right. I mean, you got the high side on the left, funky stuff, and falling off to the right. We want to be able to describe our graph a little bit more in detail than that, and having fewer classes gives us a clear-cut version of what the shape of this histogram really is. This is what I would call a skewed data set by a long shot, and we'll talk about the shapes here in just a minute. But you don't want that many classes ever. A good rule of thumb, and I'll quit talking about the number of classes, is you want let's do it in mathy terms. You want to have at least 5, I'm going to call it bins, and no more than 20 bins at all in your graph. If you have more than 20, you're doing too much. If you've got less than 5, you won't see much, all right? Or you won't see you'll have lack detail. So somewhere between 5 and 20 is a good number. I even think 20 is too many oftentimes. But if your data set's really large, and I mean really large, then 20 is not bad. Okay. Some other histograms, ways of technology that you can do. We will delve, like the ones we've been looking at so far. I've created an R. And so that's what we'll use, as well as this. We'll see some of this type or create some like this. And this is the mini tab version of it. And notice in that one, it looks like the bin widths are there. They've centered him here at 1, and that's centered at 2, and I don't like that those are centered. That makes kind of a weird graph, but Minitab, some programs kind of center numbers. So that means that if this is 1, then this is probably maybe 0.5, I don't know. They've got a weird bin selection, so it may be that the bins are broken up into 0 to half. I think in halves, because let's see, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 classes. So they got some weird class width thing going on there. And that's fine. We can kind of still see a similar shape to it, but you can alter that kind of thing there too. And we'll talk more about that later. But notice this one here was built in Excel. As I said, Excel is one of my least favorite things to build graphs in, because the graphs, some graphs are really easy to deal with. It does not really make histograms very well, and you have to kind of force it to do histograms. And then your TI calculators will also make them. I flirted with going through the procedure of how to do that. I don't think I'm going to make you guys do that for any specific reason. We're going to keep this right now to just the basic terminologies and maybe answering a few questions and some basic calculations. But I'm not going to make you build any histograms until we actually do Minitab and R. So there's also this thing called an open-ended class. All right, classes are open-ended if they have no upper or lower limit, and that's a bad thing to have. So you never want to set your data up to where you have no upper or lower limit. You want to know something about it. So sometimes you might have a question that's like, or you might question like, how many deaths are there, number of deaths based on age for specific year. In this case, this data set that I'm giving an image of is about the frequency distribution to the right, is about the number of deaths in the U.S. due to pneumonia for various age groups. And so the last category, they decided to just call 85 and older. Well, that's an open-ended class. That means that class width there is wider than all the other classes in there, and that means you cannot draw a histogram for this data. You need to know how old the oldest person was in there so you can break the data apart appropriately. And since we don't have that, we don't want to draw a histogram. So just note that when you have open-ended classes, you can't draw a graph. It's not permissible or okay to do so. So try never to have open-ended classes. This is my philosophy. We can also do histograms for just discrete values. I mean, the example we did with the emissions data was kind of continuous. They were measurements. And so we had a continuation, but you can do it with discrete values too. I mean, this data set originally here had 1,000 just numbers listed in it, and the numbers represented the number of children. So in this data set I pulled together had 435 zeros listed. So there are 435 people who said they had 0 kids from the 1,000 they asked questions to. Then 175 of them said they just had 1. 222 of them said they had 2 children, and they went on down the list. 2 poor people had 8 kids. I don't know if I could do that myself, but more power to you if you can. But notice here on the scale, instead of just listing, some people will actually come down to the midpoint of this when they make these graphs and actually list these as 0, 1, so forth and so on, so they kind of center them. But it's not really a histogram once you do that. If you want to have centered values across your bars, a better way to do that would be to make a bar graph, because we could make a bar graph out of this or a histogram, and both of them are actually acceptable in this case. So for discrete data, you could actually that's one of the few graphs you could use, because you could treat each one of these numbers over here like it was a category, and how many people fit into each category. The category is the number of children, would be 435, so forth and so on. So you could technically create a bar graph that had in this case 9 bars in it, and each one represent the thing, and it will center those values. But it's just as permissible to do a histogram for this. And your lower bounds here, this 0 really represents this bar, 1 represents this, and so forth and so on. So it's permissible to do this. Again, depending on the technology, it's easier to shift these things to be centered than others. But at the end of the day, it's really a subjective thing, and it's up to you. All right. Most of the times I've created histograms, it's very rarely for data that is only discrete. It's usually based on continuous data, but occasionally you have to have that happen. So why do we care about histograms in general, about creating them, other than trying to tell a story, right? Ultimately, for the statistician, the most important thing is what does the shape of my distribution tell me, because that will tell me what kind of statistical procedures I can now perform on that data depending on its shape. Now, is a graph the only way to look at that? No. You will probably learn in some of your other courses there are other ways to look to see if your data is skewed or not. But a graph's a good representation visually to kind of get your eyes going, oh, there's something funky about my data. Because ultimately we would like our data to be as normal, or what we call bell shape, as possible. But unfortunately, a lot of times data is skewed, in especially data that's natural data we collect in nature. It's very rarely normal. All right. And so we might get a graph that looks like the one on the left here, which is appropriately called skewed to the left, negatively skewed, or as I like to call it, just skewed left. Notice on the left hand side has all the low bars, and as we go to the right, it kind of raises up. That long tail, or the longer tail of your graph being to the left, means it's left skewed. Now this one's perfectly left skewed, so it's a little bit misleading. Not your data doesn't have to look exactly like this to be left skewed. It can have a little bit of a different look to it. I'll show you what I mean here in just a second. I'll sketch something out. But skewed to the right is just the other, or positively skewed means that your data's tail of your histogram is longer on the, so it's more spread out or falling off is more so as you go to the right of the graph, or to the positive side of your graph. If you think about the x-axis, the more positive or higher the positive number is, the more you're going off that way. So that's positively skewed. And again, those things, and I'm going to see if I can add a page real quick. Let's see, let's add one here. All right. So what I mean by misleading those two graphs, let's draw, if your graph looked like this, I'm sorry for the sloppiness of my art. I'm no by hand artist by a long shot. Notice, so say if this was your histogram, notice that while my center is not all the way, or my highest bar is not all the way to the end, to the far right of this graph, I still have this shape going on that looks like this. And there's a longer tail of this histogram on the left, so this is still left skewed. So left skewed doesn't have to be exactly like the one we saw, and vice versa with the right skewed. In other words, the high part doesn't necessarily have to be at the ends to consider these skewed left or skewed right. An example that would not be considered skewed would be what we call a symmetric graph, or a bell-shaped histogram, or what we call approximately symmetric, because really we're rarely going to get perfectly symmetric distributions. So notice that this green graph here is not perfectly what I call bell-shaped or symmetric. It's a little wonky, so we would call it approximately symmetric. All right, but notice that the tails on both ends of this thing are not as skewed as the others. It's not perfect, but it isn't too shabby either, and that's what we're kind of looking for. We're looking for the graph that's almost symmetric. Doesn't have to be perfect, but it's almost there. So this reading graphs for shapes and distributions is a little subjective, because some people would think something like this looks a little skewed, but it's really not. If most of your data is in the center of your graph, it's probably in the middle here, then it's probably approximately symmetric. It's when you have that, you can draw a curve over it and you kind of have that long tail to one side or the other, that it's either left or right skewed. Another one that doesn't come up very often but does happen is something called a uniform distribution, or one where all your bars are roughly the same height. They're not going to be all perfectly the same height, but if they're close to about the same height across the board, you're getting the same height, we call it uniform. All right, there's no real difference there. And those can also be approximately are perfectly that way, the same height as well, and so we could call it approximately uniformly distributed or whatever. This occurs more in some statistical theory areas where you deal with things that definitely happen over intervals, like things that are timed or whatnot. We discover we actually go into uniform distributions more in Math 3600 in this at the university, so I won't go into it any further here, but just know it's a thing. The last kind of definition we're going to talk about here are either your unimodal, bimodal, and there's a term I left out here I probably should include too, your multimodal. All right. So if you're unimodal, that means your graph has one distinct peak. All right, it's got to be distinct. Stands out. You got one mode, one high point to the graph. When it's bimodal, obviously the word bi means two, right? So you should have two distinct peaks. And that is your bimodal, right? You could also have something called a multimodal graph, where you have more than two peaks that are distinct. Those things are really messy data sets usually, and they're usually data sets that have been collected and then put together somehow. Sometimes you get that kind of tendency. The thing is we prefer our stuff to be unimodal because they're easier to deal with. Bimodal graphs we can still deal with, but we have to be cautious with them because they're never going to be normal at all. If you break them apart sometimes, there are methods that do that kind of thing where you can break data sets apart and investigate each part separately. If I broke those apart, I would probably call each one of those separately like approximately symmetric, and they're not bad. They're both unimodal, and maybe we can look at them differently and bring them back together somehow to kind of make an overall judgment. But we're not going to go into that in this class. Just know the difference between the two. All right, and bimodal is not always easy to pick out because it's also, again, reading graphs are subjective to the viewer. So here's an example of 3. The first one definitely has one distinct mode, right? It's got one high point, so this one's definitely unimodal. And the second one, notice it's got my little ridges here, and this one's definitely bimodal. Okay. The green graph is the one that some of you would say is bimodal, and some of you might say is unimodal. But I want to warn you against something here. The peaks have to be distinct. Distinct means they really stand out. The only one that truly stands out is this peak right here. Some people might want to call this other little nudge up here a peak, but notice it's not very different from these 2 bars on the very end. Therefore, it doesn't stand out really. All right. So this one is really doing this. It's a little shaky, but it's unimodal. All right. So enough about unimodal, bimodal. Let's move on to the next thing, and let's talk about a few other graph types here. Another type of graph that works off of these frequency distributions we've been playing with or toying with is something called the frequency polygon. And so before we actually look at a frequency polygon, I'll be honest with you, these next 2 I've only ever built to teach classes. I've never used them for anything, but they're also a preferential thing for some places in some areas where these might get used more so than others. But to build a frequency polygon, we require the class midpoints for each of the classes we've already constructed. So that's just the average of the lower class limits for consecutive classes. So for consecutive rows, we take and we average the lower class limit, and boom, we've got the midpoint. And so let's do an example of that real quick. So we would need the class midpoints to make this graph. We also would need the frequencies, but we don't need those just to find the class midpoints. So simply put, if we take the lower class limit of this plus this, we get 0.00, or just let's call them 0 plus 1. Take 0 plus 1 divided by 2, that's just 1/2, or 0.5 would be our first midpoint. And then for the next midpoint, we would take the 1 and the 2, average those, and we should get 1.5. And so from there on out, you notice that we're just doing halfway between because these are nice intervals. So we can just really add 1 to each midpoint going down, and we would get 2.5. 2.5 plus 1 gives me 3.5. So I'm just adding the class width now, just like I did with the class limits earlier in the example when we built those. I'm just adding 1, the class width I want, and that should give me the actual perfect midpoints here as I go down the list. So once you find this first one, you can just add the class width going down, and that makes it easier. You don't need to do all that formulaic stuff that they had there. Okay. All right. So, that being said, let's look at what a frequency polygon actually looks like and talk about what it is. So we needed the midpoints for a reason, right? It's because the class midpoint represents the x-coordinate, because a frequency polygon is nothing more than a line graph, and the y-coordinate represents the actual frequency, or if you want to use relative frequencies, relative frequency. And then the points are just connected with lines, and I just call this a basic line graph. I don't think it's a very good usage of a line graph, but if you go to about 0.5 here, you go up to where that little bend, the little hook is, or little elbow there is between the lines where they change direction slightly, and that should be 0.5 comma 9. This next one should be at 1.5, and that should be at the height of 26, and so forth and so on. So each one of these bins here, if you will, represent a midpoint and how they're drawing that graph. Now, how that relates to the actual histogram, it's pretty much the same thing ultimately, although I think visually the histogram is more pleasing. Here's the two graphs actually overlaid with one another, and so you can see the midpoints are just the midpoints of the actual bars here, and that's what those lines are attributing to. So they're just showing the trend of the change. It's still kind of showing the shape, but I don't like the shape of these better than the others, so I don't usually make these, but it's really preferential, up to you. You know, it's preferably how you want to do things when you're doing your own research and stuff like that. The cumulative frequency is something we haven't discussed before, but it's something that's kind of simple and makes kind of sense. But the cumulative frequency is just the sum of the frequencies for the class you're interested in and all previous classes that came before it. So it's just a summation of the classes. And so as you notice here, there's nothing to sum to for the first frequency, so it's just 9. If I take 26 and add 9 to it, I should get 35. If I take 11 and then add 35 to it, which is the previous sum, I should get 46. If I take 13 plus 46, you can see where we're going. We're just adding up. We're adding each frequency to the next to get the next cumulative frequency, the total of that frequency plus all the ones that came before it. And at the end, we should get the grand total of the sample size. And remember, with the emissions data set, which is what this data set's representing here, the grand total of all the frequencies was 65. So the last value there should be 65, or should be whatever your sample size is, depending on your data set. So I've never made this. This is useful for creating what they call an ogive, pronounced O. Ogive. Those are back in the 70s, as some people might I like to refer to it or think of it as an ogive turkey. But an ogive, nonetheless, is a graph that I just have never really seen used very many places. The only place I can imagine it being useful in is in business presentations to show increasing trends or changes over time, because you want to show how things are growing from one point to the next over a range of data. But even then, I think there are better graphs to do that than this one. This is probably one of my, other than the pie chart, this is one of those graphs I just go, okay, we made that graph. I probably won't show you how to make this graph in R. As a matter of fact, I cheated and just took the image out of a book. And so I'm not going to require you to make one, but I want you to know what they are, how they're built, and know what a cumulative frequency is, because there are other types of graphs that use cumulative frequency as well, that come in handy from time to time when you're comparing more than one group. But the ogive is basically, its x value is the class upper limit, which is weird already, and then the y coordinate is just the frequency again, or the cumulative frequency in this case. And so you can see how it adds as you go from left to right, which is great and all. But I guess you could see, like, from the value 0 to 1.99, it grew pretty fast. And you can kind of see that most emissions were below 3.99 here. So I guess that's one useful thing. And there's very few that are above, because we didn't add much to it. So you can read this graph. But again, I still think the histogram is probably the way to go. And in the frequency polygon, at best, might be the second best way to go with these. But ultimately, we will discuss one other type of graph where you can see sort of trends, but not as in detail as this later in the semester, that you may also be familiar with. But we'll get to that when we get to it. Anyway, gang, hope everybody's doing well, and I'll talk to you later.